Hello, everyone. Welcome to PO. My great pleasure today is to introduce Katherina von Dichter from the Technical University of Munich. She's going to tell us about inequalities for symmetrizations of convex sets. Katherina, please.
Okay, so thank you for inviting me, and I will go on with my topic. So this is a giant work with René Brandenberg and Bernardo González Merino. Both of them are my PhD advisors. So I'm doing my PhD at the Technische University of München. And we will start off with the motivation. So the motivation I will present here is some basic, and it's the average length. So imagine you are in the mountains and you are going uphill, and then you want to measure the length from the down point to the top. For sure, you will use the gauge function. So you take the down point as x, the up one as y, and then the distance will be measured as the gauge function of x minus y. With respect, for example, some c. You can take c as a Euclidean ball, then it will be just a Euclidean norm. Or you can take any other gauge bodies that you want. But let's go on with some definitions, and then we see why it is interesting to consider that our gauge body may also be non-symmetric. So the first definition that we need is a Minkowski sum. The Minkowski sum of two sets A and B is just a vector sum of any point A from A and B and from B. Here is an example of taking the Minkowski sum of a yellow triangle and a blue triangle, which ends up in a hexagon, which is here green. Another definition that we need is a polar body. The polar body is something like taking the inverse of a set, and is defined as a scalar product of A and X, which is less than or equal to 1 for any point A from K. Here down you have a picture of 3 examples of some polar bodies. The first one is a simplex, S3 simplex. The polar body is a rescaled and rotated version of itself. And here you have 2 other basic examples of the polar bodies. The polar body is something like taking the inversion, because the idea of it, when you take a Euclidean ball of radius r, then the polar will be against the Euclidean ball, but the radius of it will be 1 over r. So it's something like taking the inverse of the distance to the boundary points. So let's return to the example with the mountain. Here we have the point x, this is the point down, and y is the point up. Since we are going up in the mountain, the distance from going uphill and downhill is not the same. So probably we want to take as a gauge body something not symmetric. So not, for example, a Euclidean ball, but like here, a simplex. So in the planar case, let's take a triangle. Then taking the distance from x to y, so the gauge from x to y with respect to c, is not the same now as the one from y to x. Actually, the gauge function of the y to x is the same as taking the x minus y with respect to the minus c. Minus c is taking your gauge body and rotating it by 180 degrees. And you see actually that in this example, those 2 gauges are not the same, and they have, so one is twice of the size of the other one. But now you end up in the problem that you have that the one of c and the minus c is not the same. So you have now the 2 measures, and you can take symmetrizations of them. The first natural symmetrization is taking maximum of these 2 gauges. If you take maximum of the gauge with respect to c and the one with respect to minus c, is the same as taking the norm of x minus y with respect to a new set, which is c intersected with minus c. And this one is now symmetric, so this is really a norm. But you can take another symmetrization. What if you take just the arithmetic mean of these 2 gauges? This corresponds also to a norm, but to a new norm. This is a norm that has as the unit ball this new set, which is c polar minus c polar over t2 and taking again the polar. Remember that the polar is something like taking the inverse. So this corresponds to the harmonic mean of C and minus C. But you could also think, why not taking now the norm with respect to just C minus C half? Actually, this one cannot be represented as some average of the gauges of C and minus C, but it's also a natural symmetrization. In a similar way, you can take the norm with respect to the convex hull of C and minus C. This is needed because we want always that our bodies will be convex. Here on the picture, you see all these symmetrizations for this triangle. So the blue hexagon corresponds to the triangle intersected with a minus itself. Then the orange is the harmonic mean, the brown is the arithmetic mean, and the green is a convex hull. And we see now that all of these norms are different. So let's start with the basic. We have the arithmetic harmonic mean inequality, which we can extend with a minimum and maximum. Here A and B are just positive numbers. This can be extended also for convex sets. So if A and B are convex sets, then in the 1961, Führer has shown that we can also get a chain of the inequalities where we have A intersected with B is the minimum of A and B. Maximum corresponds to the convex hull. Then A plus B over 2 corresponds to arithmetic mean of A and B. And this term, the one that is left, is the harmonic mean of the convex sets A and B. We know that the mean inequality for numbers is best possible. What about the one of Führer? Is this inequality, this containment, best possible, or can it be improved? To understand it better, we have to introduce a notion that is called the optimal containment. So we have two sets, K and C, and we say that K is optimally contained in C if, first of all, K is contained in C, and also there is no smaller escalation of C which completely contains K. Then we say that K is optimally contained in C. We are able also to characterize this optimal containment. So we say that K is optimally contained in C if and only if we have enough touching points Pj between K and the boundary of C, and they are well spread, meaning that 0 is contained in the convex hull of the outer normals of them. Here is an example, the picture. We have that the black set is K, which is optimally contained in the blue set C. And we have the touching points P1, P2, P3 between the boundary of K and the boundary of C. And if you check the outer normals of this at this point, they all have 0 contained in the convex hull of them. So let's return to the chain of Führer. The chain of Führer was introduced for the general sets A and B, but since we want to talk about symmetrizations, we only consider sets C and minus C. So now we have 4 different symmetrizations: the minimum, the harmonic mean, the arithmetic mean, and the convex hull. All of these symmetrizations are convex sets, and they're also symmetric. They are all ordered by Führer in this chain, and we can show that the minimum is optimally contained in the harmonic mean, and the arithmetic mean is optimally contained in the convex hull. Here is an example for the triangle, where you see again all these intersections. So the blue is the minimum, is optimally contained in the orange, and the brown, which is the arithmetic mean, is optimally contained in the green, which is the convex hull. But what about the other inclusions? Are those optimal? Like you have seen on the picture before, probably that's not always the case. So for the triangle, you have seen here that the orange is not optimally contained in the brown one. So there is room for improvement. So to go on, we need to introduce some measure. This is the Minkowski asymmetry measure. This is a factor S of C for a convex set C, which is the smallest resolution factor rho, such that C is contained in rho times minus C with a suitable translation. And this translation is called the Minkowski center. If we say that C is Minkowski centered, means that the origin is a Minkowski center. On the picture, you see that K, the triangle blue, and minus S times K, the triangle red. So the first thing to consider when we're talking about the containment of this means is the case of the simplex. If we take S to be the Minkowski-centered simplex, then we can see which containments are optimal and which are not. Here we have different cases for n to be odd and when n is even. When n is odd, for the simplex, we have the intersection is optimally contained in the convex hull, which means that in the case when n is odd, for the simplex, all of these means are optimally contained in each other, because the minimum is optimally contained in the maximum, so those in between are also contained optimally in each other. When n is even, we have a different situation. Then the factor that we actually need is n over n plus 1, which is obviously less than 1. We can also calculate the factor that we need between the two other means, which is the harmonic mean and the arithmetic mean, and this is given here. So again, to the picture, in the second part, the factor n over n plus 1 is a factor that we need to rescale the blue hexagon in the green hexagon. So here we have some inequalities for the reverse case. So here represented as the forward case where you have minimum, harmonic mean, arithmetic mean, and maximum. We can also think which factors do we need to get the reverse inequalities. And here we present the reverse inequalities where we can connect any two means with the help of a factor which only depends on the measure of asymmetry. So for example, the first one, maximum, is optimally contained in S times the minimum. Or the second one, maximum, is optimally contained in 2S over S plus 1 times the arithmetic mean, and so on. So we are able to connect all of them. And those are always optimally contained. Let's consider the sixth, the last part. We see that here we have the arithmetic mean and the harmonic mean. And we have also that the arithmetic mean is contained in S plus 1 over 2 times the harmonic mean. But so this containment is not optimal, which means for any S, we can show that we can find some convex set where we have the optimal containment, but that's not always the case. And this is the only case where we don't have the optimal containment for the reverse inequalities of these means, which is quite surprising. Okay, so here is a smaller application. So here is a reminder, if we have the 1, 2, and for example, the infinity norm, we can write the inequalities of the norms in the forward and in the backward direction. In the forward direction, it goes very simple, and in the backward direction, we just need the factor square root of n and n. Now, let's consider the symmetrizations and obtain similar case. So we have that the means. For the means, we have in the forward direction the first line of inequalities. Here you see that the norm of with respect to the maximum less than or equal than the norm with respect to arithmetic mean, less than or equal to the one of the harmonic mean, and less than or equal to the one of the minimum. And also from the result for the reverse direction, we can get the change of this inequality for norms for any 3 of them. And as an example, here you see the symmetrization for the simplex in the dimension 3 with all the corresponding colors. Okay, so if there are no questions, let's go on. So we have considered how we can relate all these means in the backward direction. What about the forward direction? In order to understand what happens in the forward direction, we have to be able to give us the characterization. And this is this theorem. It says that the minimum is optimally contained in the maximum if and only if the harmonic mean is optimally contained in the arithmetic mean. And this happens if and only if we have the following situation. We have 2 hyperplanes supporting our set C from 2 sides. Those hyperplanes are parallel, and the points of C where it supports are P and minus P. This is important. So for example, if you think about a triangle, you can always take a triangle and support it from both sides with 2 parallel hyperplanes. But you will be not able to do it in this way, such that you will have points P and minus P belonging to those 2 parallel hyperplanes and to the boundary of C. Okay, so this was a characterization. Now, so we want to have the optimal containment between these means. This is why we define the parameter alpha of C. Alpha of C is a parameter such that the minimum is optimally contained in the convex hull, so in the maximum, multiplied with this parameter. For sure, this parameter is always greater than 0 and is always less or equal 1. Less or equal 1 follows from theory because the minimum is always optimal, is always contained in the maximum. And then we can also take this alpha 1 and alpha 2, the lower and upper bound for the parameter alpha. And here we have a nice diagram that shows all the possible values of the parameter for the planar case. So let's go through the diagram. On the one side, we have the symmetry S. The symmetry S is bounded from 1 to n. In the planar case, it's 2. And we have 1 is if and only if the set is symmetric, and n if and only if the set is a simplex. For the values alphas, we have all this yellow region. The lower bound is 2 over s plus 1, while the upper bound is more tricky. The upper bound is equal to 1 for all the symmetry values from 1 to phi. Phi is the golden ratio, and then it is s over s squared minus 1. And we can go through all the lower bound and the upper bound. And I will show you which sets fulfills this with equality. So which set reaches the lower and the upper bound. So for the lower bound, we can take our S, which is our Minkowski-centered regular and simplex, and then we intersect it with a rescaled and rotated version. So we take S intersected with minus S times S, like on the picture. This is intuitively taking a simplex and cutting off in a nice way all the vertices. And for this set, we have the optimal containment between the minimum and the maximum with the factor 2 over s plus 1, which corresponds to the lower bound. This s can be taken from any value from 1 to 2, and so we can fill out all the lower bound with this construction of this family of set. Here I have shown to show you a picture about how looks all the symmetrizations for this construction. So you have that the black dots are the vertices of the convex of the intersection of C and minus C. So the convex hollow of these dots. The yellow one corresponds to the harmonic mean. The blue one corresponds to arithmetic mean. And the red one corresponds to the maximum. So what this one says, it says that taking the black dot to be optimal contained in the red one, you need to rescale the red shape by the factor of 2 over s plus 1. What about the upper bound for the value of the parameter alpha? For this, we can take a construction that is a pentagon, like on the slide. This pentagon we call the house for its shape, and we can show that the minimum is optimally contained in the maximum with this factor. And here we have also all the symmetrizations now done for the house. So again, we have the yellow one is a harmonic mean, the blue one is the arithmetic mean, and the red one is a convex hollow. So let's also talk about the black dot, the red dot. The red dot is the maximum value of a symmetry S such that alpha can still be 1. Alpha is 1, meaning that the minimum is optimally contained in the maximum. And we have shown that if C is planar and Minkowski centered and alpha is equal to 1, then the asymmetry is not greater than the golden ratio. And if we have the asymmetry exactly as golden ratio, so we are exactly at this red dot on the diagram, then the set must be a linear transformation of the golden house. The golden house is a pentagon that is shown here on the slide. The important part here is that the origin is at the end of the walls, and also, like you see, we need the proportion from the height of the walls to the height of the roof. So the golden house is this pentagon, which is on the picture black. So this is an interesting construction because this construction is the one with the highest asymmetry such that the minimum is optimally contained in the maximum. So I want to give you a short idea about the proof of it, just from the picture without going into the details. First of all, we know that we want the minimum to be optimally contained in the maximum. So we use the characterization, meaning we have two supporting parallel hyperplanes, which on the picture is minus h and h. And our set C must belong in the area between these two hyperplanes. We also know that we have the touching points minus P and P, which belongs to the hyperplanes minus h and h correspondingly and must belong to the boundary of C. What we also know is that C is Minkowski centered. So using the theorem of the characterization of the optimal containment, we know that we have the touching points between C and minus S times C. Here on the pictures is Q1, Q2, Q3. Collecting all this information about the dots, we now get some interesting regions for the points minus S times Q1, minus S times Q2, and minus S times Q3. All of these points must also belong to the set C. And then checking which shape must have the body with the highest asymmetry, which will fulfill all these restrictions, we end up in the unique situation. Namely, we have a pentagon, which is here on the picture blue. And we can show that this pentagon must be a linear transformation of exactly the golden house. This was all about the planar case, but we can also think about the same construction in the higher dimension. So we take n to be greater or equal to, and then we take the same idea, we take an n simplex, and we cut off the two vertices with two parallel hyperplanes, h minus and h plus. So we have done this construction, and we calculated that then the symmetry must be given like is on the slide. So for the golden ratio, you know that you can obtain the golden ratio from the proportion, or solving the quadratic equation x squared minus x minus 1 is equal to 0. Taking now this factor that we obtained from the general golden house, we can also obtain it solving a quadratic equation, which is x squared minus n minus 1 times x minus 1 is equal to 0. So you can consider now this factor as the generalized golden ratio for the higher dimensions. Okay, let's go on with another topic, which is also related to all these means. This is the constant width sets. The constant width set is an interesting construction of sets which are round. So if you take this set and place it between two parallel hyperplanes, then it will roll in any direction like you want. This means that the breadth of the set is equal in any direction. So here is a formal definition of the breadth. The breadth of the set K with respect to another case, set C, is given by the fraction of the support function of K minus K over the one of C. If you're talking about the constant width sets, you want that the breadth will be equal in any direction, right? So you can define the minimal breadth, which is the width, and the maximal breadth, which is the diameter. And when it's constant width, meaning that all the breadths are constant and the width is also the diameter. And this is also equivalent that the K minus K over 2 is equal to C. Usually when you talk about constant width sets, you take C as the Euclidean ball. But this case is not the only one, and we now consider C to be just a symmetric convex set. So to characterize the constant width sets is not that easy, but we have some properties. So we know that for any constant width sets, we have fulfilled that they are also complete sets. Complete set is a set such that if you take any point which doesn't belong to the set and add it to it, takes a convex hull with it, then you increase the diameter. So here you have an example of the Rouleau triangle. The Rouleau triangle is a triangle where you put on each side an arc, and this set is of constant width with respect to Euclidean ball. It is also complete, meaning take any point out of the set, add it to the set, and then in this corresponding direction, you will increase the diameter. For sure, we talk here about C to be the Euclidean ball, and in this case, the notions of constant width sets and complete sets is the same. It also happens, for example, for the planar case. But in general, those are not the same. But the advantage of the complete set is taking any set K, we are able to perform a completion of it. So we know a complete body, so a body that is complete with respect to this given C. And what is interesting to understand is how different are those bodies. So for constant width sets, you have that the width and the diameter is the same. But what happened about complete sets? How big can be the difference between the width and the diameter? And this was answered quite recently in 2018 by Richter. And he has proven that if K is complete with respect to C, then the ratio of diameter over width is bounded by n plus 1 over 2, where n is the dimension. He has also shown that this bound is sharp when n is odd and asymptotically sharp when n is even. This was performed by taking K as a simplex and C as the simplex in the set with a minor simplex, and he has shown this bound. We can improve this bound by using some things that we have shown about the means, and also by using this asymmetry threshold of means. So we defined this asymmetry threshold of means as following. So it is the smallest number such that there exists no Minkowski set C with the asymmetry value which is greater than this gamma, and such that you have that the means are optimally contained in each other. For sure, we know that this must be smaller than n, because for n, when s is equal to n, we have the case of the simplex, and we know that for the simplex, the means are not optimally contained in each other. But we also know that this value must be greater than n minus 1. N minus 1, we can take the set C as a cylinder, and then you don't have, so and then for this one, you have optimal containment between those means. So gamma must belong somewhere between them. And here is the theorem. The theorem says if K is complete with respect to C, and we have that the symmetry value of K is S, then this ratio of the diameter over width is actually less or equal S plus 1 over 2. Remember that Richter has shown that it's less or equal than n plus 1 over 2. We know that the value of asymmetry is from 1 to n. So we have exactly the bound n plus 1 whenever s is equal to n, and this happened only for the simplex case. Moreover, we know that for any asymmetry from 1 to this gamma of n, which is the threshold of asymmetry, we can find the case of equality. And separately, we have shown that this threshold is equal to n when n is odd, and also that is greater than n minus 1 when n is even. And we have even been able to show some smaller interval where we can find gamma of n for n is equal. So the idea of the proof is based on two things. First, we use the property of K being complete, and then we are able to show that we can take that the diameter is actually s plus 1 over 2, the half diameter, sorry. And also that the width of K with respect to C is greater or equal to the one when you replace C with a mean of K and minus K, which is the minimum of K and minus K. And then you get here that this bound can be obtained from one of the parameters that you need between these two symmetrizations, namely between the minimum and the arithmetic mean. And by calculating this parameter, we were able to show this theorem. And the last part about the complete sets is ongoing research, and we are working more deeply into these topics. So this was everything. Thank you for your attention.